This is October 30th, 2019. This is video number 5 to introduce my new book, For the Sake of Civility. Also, a book I did just prior to For the Sake of Civility, which is Existence Uniformity, which includes all of my best content from my website for several years. I started the website in 2008, and then I started a Facebook page in 2012, If Matter Were Eternal, and I mainly worked on, put my content on If Matter Were Eternal since then, but there was a lot of stuff developed on both web locations, and Existence Uniformity includes a lot of the best early stuff I did and some of the best later stuff I did. And it also shows how my particle system was developed at the early stages of that led to the 2017 materialist naturalist periodic table that explains atoms in terms without the existence of negative charge. Okay, this video is going to speak to the topic of newtons as a way to quantify push force and attraction force. Later in the video, it's going to discuss surface gravity of a planet. That is approximately 9.8 meters per second on Earth, and that is approximately 3.7 meters per second squared on Mercury, and it's just a little bit more on Mars, even though Mars has roughly double the mass of Mercury. Its surface gravity is 3.72 meters per second squared. And once again, it's meters per second squared. It means it accelerates that much each progressive second, not that it's falling at that rate. A newton is the amount of force necessary to move a 1 kilogram object 1 meter in 1 second. It is implied that there's acceleration, so this must be why you take the meters per second is squared in the equation for newtons. A newton, however, can also be quantified in pounds of force. If you had a 1 pound sphere sitting on this table and only the very bottom of the sphere would be pressing down, it would be exerting 4.4448 newtons. So what you come to realize is that a newton is approximately 1/4 pound of force, and Earth's surface gravity. The Earth's surface gravity is 9.8, roughly 9.8 meters per second squared. What that translates into is when you drop a body, object or whatever, in Earth's gravity close to the surface, it's accelerating the whole time. In the first second, well, let's just say it's 10 meters per second that it's accelerating. And it's not falling 10 meters per second, it's accelerating 10 meters per second. So what you have in the first second, it falls 5 meters. In the second, it has fallen a total of 20 meters. In the third second, by the end of the third second, it has fallen 45 meters. By the end of the fourth second, it's fallen 80 meters. By the end of the fifth second, it's fallen 125 meters. And there's a real simple equation for determining that. In Earth's surface gravity, that's what pulls down on this 1 pound ball or quarter pound sphere that would be equivalent to the force exerted that we would call 1 Newton. It sounds like more force when you talk about this. You think of it as 1 kilogram being approximately 2 pounds, and that the force needed to move that 1 meter, which is about 3 feet, in 1 second. You know, it's a decent amount of force, but I would like to speak of newtons as being not only the force to move, say, a kilogram 1 meter in 1 second, which implies acceleration, but it's also accepted in science that it's this quarter-pound sphere, let's say, the amount of force being pushed down on this table by that, and that's continual. So newtons could be continual force, like your body via the Earth's gravity and your body reciprocating gravity with the Earth, pulling, you know, your whatever number of pounds you weigh. That force is being exerted on your feet when you're standing up. But newtons can also be thought of as when a baseball bat hits a baseball. There's a certain number of newtons in a split second when that collision occurs. So it's not ongoing. And then the baseball, say if it was a home run, maybe it moves at 110 or 15 miles per hour and goes out of the park or across the fence, home run fence. But those would be newtons as well, and that would be just a momentary collision or force. That should be able to be quantified as well in newtons. Then you have pull force. Let's say you take a belt and you put around an object and you're pulling it toward you. This would be pull force. And so and this is like gravity. The number of newtons and you have push force, you have continual push force, you have momentary push force, and then you also have pull force. And it would be in terms of described in terms of newtons as well. Okay, so the same thing would apply. There's a page in existence uniformity that goes into this. Pretty early in the book, and it describes the attraction force using Newton's equation that is being exerted between celestial bodies in our solar system. And let's see here. Here it is, this page. I've also got this up at the Facebook page, If Matter Were Eternal. For example, during a conjunction between Jupiter and Saturn, if you use the equation here, which is really developed upon what Newton taught regarding gravity, you would come up with a gravitational force due to the distance and their mass, Jupiter and Saturn, for however long a conjunction lasts. You come up with an amount of 11.2 billion newtons of attraction force. So there is some slowing that can occur. There's actually some speeding up that can occur relative to Mars in relation to Jupiter during conjunctions. That would work differently than Jupiter in relation to Saturn, which actually slows Jupiter. But anyway, one of the reasons we have relativity is because all of the bodies, and you've got to remember, one of the main principles of relativity is that all objects, regardless of mass, fall at the same rate. And so you get that implied when you look out at these different mass bodies in our solar system, and they all orbit as if the mass of the secondary body, that planet, has no effect on their orbital velocity. Only the sun's mass. They always, the way it's done right now, they cancel out the M2 mass, the secondary body mass. It's not factored in when they are finding either gravitational force, if they want to do that in newtons like I'm doing, or especially if they are assigning orbital velocity. But what's actually causing those uniform velocities as if they all have the same mass, whether Mercury, which is a very small planet, or Jupiter, which is a very large planet, is that these conjunctions are slowing. Over time, they've slowed some down. They've actually sped up a few, like Mars. And so it gives the appearance that it doesn't matter. The mass of the falling object doesn't matter. That's what was implied. And that had a huge influence, apparently, on the perception that relativity was necessary. In the remainder of this video, I'd like to discuss surface gravity and how that relates to relativity and what it implies about relativity, which apparently has been missed. First of all gravity is reciprocal. There's no gravity expressed when you have a large gravity source like the Earth, let's say, and then something without mass is close enough to it to be affected, but it doesn't have mass. No mass, there's no effect. There's no gravity being expressed. To literal space, gravity has no effect on literal space. It's empty. Now, in comparison to that, gravity does have a reciprocal, the Earth has a reciprocal gravitational relationship with every object that has mass. Objects include 1 kilogram balls or cubes, a person's body, both can be dropped and accelerate toward the Earth at 9.8 meters per second squared, or even a dust particle, which, because of the atmosphere's resistance, it may sink to the surface of the Earth, but that resistance keeps it from falling at 9.8 meters per second squared. Now you have also the objects with mass that are gas molecules. They have mass. They would be escaping to space. Some probably do, a few of the lightest ones, but the ones that are being held there in our atmosphere have a gravitational relationship with the Earth. Anyway, surface gravity, what it indicates is the strength of the gravity from that primary body, well, in that case, secondary body, being Mars, Mercury, Earth, Venus, etc. They're a secondary body because they orbit the Sun, which would be the primary body in those relationships. But they are primaries when they have moons that are orbiting them, like the Earth has a moon and Mars has a moon, a couple of moons, small moons. Venus doesn't, and nor does Mercury. But anyway, the strength of the gravity of Mars is much less than that of Earth. A person would be much lighter if he were standing on Mars in comparison to Earth. If you had a scale, you would show that you weigh much less on Mars. The same goes for Mercury. Mercury's surface gravity is 3.7 meters per second squared. That's less than half of what the surface gravity is on Earth. Things would fall if they're dropping through the area right above its surface. They would fall much more slowly than objects falling just over the Earth's surface. The surface gravity of Mars is just a little stronger. Even though the mass of Mars is about double that of Mercury, its surface gravity is only 3.72 meters per second squared. Okay, all gravity is reciprocal. That means, once again, that it takes two objects with mass for gravity to be expressed. And whenever you increase the mass of the secondary, well, you can increase it so you don't have a secondary. You could have two bodies that are of equal mass orbiting one another in this way. Now, the orbits of the planets in the solar system do cause the Earth, or excuse me, the Sun to wobble. Okay, so that is being that changing of the movement of the primary body is occurring here too. It's really pronounced with the moon Charon orbiting Pluto. But this carries over. See, it's believed right now that the mass of the secondary body in an orbit has no effect on its orbital velocity. That would mean that if Jupiter were at Mercury's distance from the Sun, the Jupiter, according to relativity, should orbit with the same velocity as Mercury, but that's false. We know, we've observed other planets in this solar system, in this galaxy, other solar systems, where there's been some planets much like Jupiter, let's say, very large planets, that are orbiting close to their star, and they make a complete orbit in 3 days. Now compare that to Mercury taking 88 days. It's very small. It's not a very massive body. It takes 88 days to make a complete orbit around the Sun. Its period is 88 days. Now you'd have to, of course, determine how far these bodies that are orbiting their stars in 3 days are from their primary bodies that they orbit, their stars, and you'd have to determine how massive those stars are, and do all those comparisons. But I'll guarantee you that that if you drop two bodies of enough contrasting mass in the Earth's atmosphere through space, that if you give them enough time to fall, that the more massive body, when falling toward a gravity source, will pull ahead a little bit of the much lighter one. And this can be demonstrated in all kinds of different ways. Okay, I could go into all kinds of examples of this, but once again, those gas atoms in our atmosphere are not falling to the Earth but yet they have mass. They're being held in place above it.